Okay, the class gave me a list of exponential equations that they would like to see solutions for. So I'm going to work my way through them one at a time. Also, this one here, I've added a part B where I've changed the base. And this question here, question 5, I think the student was just being cheeky. I'm going to do that one last, so you can just stop it when I get to that, because it's not really part of the skills we've been practicing, but we can solve it, and I will show you how. Okay, so before we get started, my suggestion always when you're working with exponential equations is you take the time to write out a list of increasing powers of these numbers here. So starting with 2, 2 times 2 is 4, so 2 squared is 4, 2 cubed is 8, 2 to the 4 is 16, and so on. So I've written out a list here. And you're going to see the usefulness of that list in a minute. You might want to pause it, copy that out, and you can also extend this list as well. You can extend it quite easily. The number that would go here is 3 to the exponent 6, which is also 243 times another 3. Okay, so the first question I was asked is 45 to the exponent 6x minus 3 is equal to 45 to the exponent 8x minus 6. Now this may at a first glance look a bit messy, but the root of this is actually very simple. If 45 to this exponent is equal to 45 to that exponent, we can deduce that this exponent is equal to that exponent. Let me just show you in the simplest case I can imagine. If we have 2 to the exponent x, and we say that that's equal to 2 squared. 2 squared is 4. 2 to the x is equal to 4. We can guess and check and quickly determine that x must be 2. Because that will make 2 to the x, 2 to the 2, which is 4 as required. So all we're doing is we're looking at our two sides, and when we see that the base is the same, we can deduce that the exponents must be equal to each other. So I'm going to do that here. On both sides we have a base of 45, so we can deduce that the exponent 6x minus 3 is equal to the exponent 8x minus 6. We're then going to bring all of our variables to one side, all of our numbers to the other side. So I'm going to subtract 8x from both sides. I'm going to add 3 to both sides. And if we divide out the minus 2, there's our solution. And if you want to be sure that you have it right, you can take 3 over 2, sub it in here, take 3 over 2, sub it in there, evaluate it, and both sides must come out the same. Okay, question 2. And question 2, they've asked 16 to the exponent 2x is equal to 1 over 16. Now I'd like to apply this. I would like to immediately say the exponents are equal to each other because the bases are the same. However, these bases are not identical. They're similar, but here the base is 16, here we have a 1 over 16. So I'm going to apply this well-known exponent rule. And I'll make a video deriving all the exponent rules afterwards, but we will accept it for now as we're solving this. 1 over a to the n is equal to a to the negative n. That means that we can replace a fraction with a negative exponent. So here I have 1 over 16 to the exponent 1. I can write that as 16 to the exponent negative 1. Now I have identical bases. So I can say this exponent is equal to that exponent. Okay. I made a slight modification to this question because these often come up. So for question 2, I've made up question 2 part B, and this is 8 to the 2x equals 1 over 32. Now remember, in our past questions, we had an identical base, and with identical bases, we could say that the exponents were equal to each other. And I would like to apply that here. This is where my list of numbers is going to come in. I see an 8 and I see a 32. And after you've worked with a lot of these, you're going to recognize which numbers go together and how. But until then, just have a look at this list. So we're going to look for the numbers 8 and 32. Can you see them? The 8 is here, and the 32 is here. What this list tells me is I can write 8 as the third power of 2 and 32 as the fifth power of 2. So I'm going to use brackets to make sure I get everything right, and I'm going to replace 8 with 2 to the exponent 3. And I'm going to replace 32 with 2 to the exponent 5. I'm now going to use a couple of exponent rules. One of them allows me to multiply these exponents together to bring this exponent into here. So I have 2 to the 3 times 2, which is 6x. And that's equal to 2 to the negative 5. Now I have identical bases. And with these bases identical, I can just say that 6x is equal to negative 5, or x is negative 5 over 6. Okay, the third question is quite similar to that. It'll require one more step though. Let me write it out clear so you can see it. So we have 64 times 16 to the x, and that's equal to 1 over 256. What makes this different is 16 is being raised to this exponent, but then it's also being multiplied by 64. Now the way I'm going to deal with this is I'll divide both sides by 64 to make it look more familiar, more like this question here, where I simply have a base raised to an exponent on the left, as opposed to a base raised to an exponent and then all of that being multiplied by a number. So we have 16 to the x, and I'm going to divide both sides by 64. So that's equal to 1 over 64 times 256. So you can use your calculator for this, save some time. 64 times 256 is 16,384. So I have 1 over 16,384. That's equal to 16 to the x. Now I'm going to look in my list of numbers. I'm looking for a 16 and a 16,384. Now, as you can see, I don't have the number I'm looking for. I have a 16 here and I have a 16 here, but I don't have a 16,384. So I'm just going to continue one of these. I'm going to start with this one. I'm hoping that that comes out as a power of 4 because I'm not going to have to do that many of them. So I'm going to take my 1024 and multiply it by 4. That gives me the next number here. This is 4,096. I'm then going to multiply 4,096 by 4, and now I have the 16,384. And that's the number I was looking for here. So what this list tells me is I can write 16,384 as 4 to the exponent 7. So I can replace this with 4 to the 7. And you can verify that for yourself with your calculator. 4 to the exponent 7 is 16,384. The reason why I tried that list is I also already found 16 right here. 16 is 4 squared. So I'm going to replace 16 with 4 squared. And now I have 4 to the 2x is equal to 4 to the negative 7. This makes 2x equal to negative 7, and when we divide both sides by 2, you'll have x is negative 3.5, or negative 7 over 2 if you prefer to write it as a fraction. Okay, the next question on the list I'm going to leave until last, so you're welcome to stop the video before that. Actually, we're near 10 minutes. We're at 10 minutes, so I'm gonna make that on a second video. We'll run through the last one really quick. The last one is 2 to the 2x plus 1 is equal to 2 to the 5. Simply 2x plus 1 is equal to 5 because we already have the same base. That makes 2x equal to 5 minus 1, which is 4. If we divide by both sides by 2, you'll see that x is equal to 2. And I suggest, again, while you're working with these, that you keep a list of increased powers. You might want to pause it there and copy this out. Keep a list of powers in front of you so that you can very easily find a common base for pairs of numbers. Now, this, to be honest, is kind of a useless skill because it'll only solve problems made in a textbook so that they can be solved this way. Real problems require logarithms, and that's what I'll show you in the next video.